I'd like to welcome you to the, oh, don't want to do that, don't want to leave, to the crop modeling webinar. I'm going to X my thing out of the corner. No, don't want to do that. There we go. I was trying to avoid blocking the screen out. Okay, the steps that you need to do and include a number of steps prior to addressing the 4 core questions. And you're all familiar with calibrating the cultivars from experimental data at sites nearby, and it's not necessarily at this farm survey site. In fact, it will not be. You need to do work to set up your very first set of historical simulations with the farm survey, and this is basically 1 or 2 years, anywhere from 40 to 200 farms. In order to do that, you need to describe sources of soil information, management, cultivar, and do work to verify that the models are reproducing the distribution of yields that exist in the farm survey yields. That's important. Even though the economists want the change ratio, I think it's important for realism, and to some extent, whether you're mimicking high yields or low yields or responding right to water or nitrogen, also affects the CO2 response. We'll talk a bit about simulating RAPs, the technology trend in yield, simulating climate adaptations, and then discuss planning for the CTWN for single farm sites. We would like to have each of the teams come with data ready to run for the CTWN on specific crops. I'll show some example graphs of what I think these will look like for output. And we hope to actually complete the simulations at the workshop and come up with a plan that's designed for at least 2 papers, 1 per crop, say 1 on maize, 1 on rice. So that's a preview of where we'll be going in this presentation. I'd like to review a little bit the difference in a couple of definitions. I know you may have seen these before, but the RAP, the representative agricultural pathway, is what will be going on even without climate change. And this includes future yield trends, which basically will be coming out of, say, fertilizer and cultivar improvement, management improvements, and then there'll be other issues with labor and price and the economic structures. And you need to see this as a little different from major climate adaptations, where you might actually need for a country to do major investment, policy change. Now, some of those may lead to new cultivars or agricultural management policies, such as bringing in irrigation system, but they are different. So what's called key differences basically reviews what I just stated at the first start. Now, the point here is that this time we will be trying with the crop models to actually implement what will be in a RAP, and that's new compared to the prior phase 1. So this is from a crop modeling standpoint. The technology trends and climate adaptation will be decided very much with joint engagement with stakeholders, economists, the impact model projections, the agronomists, and plant breeders. And the economists may do other aspects of a RAP beyond what the crop modelers do, but they will be responsible for that aspect. Now, on the left, I've listed some elements that would be in a RAP. Say, in the future, farmers may be using a higher nitrogen fertilization rate. Sowing date is already handled with a planting window, so that will not be changing. The cultivar may be improved in terms of higher yield with a higher radiation use efficiency, greater grain number. You may have a longer filling period duration, but I don't want you to change cultivar life cycle for the RAP. Maybe a higher plant population or phosphorus fertilization. On the other hand, a climate adaptation will be a little more of a heroic effort to come up with heat-tolerant cultivars that don't exist now, drought tolerance, flood tolerance. You shouldn't, if you have a new irrigation scheme, that will involve investment on the farmer's part or the country. So that does not belong in necessarily a RAP, although we know that will change. We would like to envision improved cultivars that adapt to climate change, and one of the first ones is to bring back the life cycle, and that's in the asterisk here. The goal on that one is to reproduce the same season length that actually existed under the current climate. It will take a little bit of work to come up with that. Now, crop selection is not really something farmers do. This is what the economists would switch from, say, maize to sorghum or some other crop. Drainage is a costly component, so it involves investment. Residue management may be part of no-till farming and new disease pest management. Okay, so before we go into the core questions, I want to identify the 7 crop model simulations that will be done. What Cheryl Porter called CEM0 is basically the historical farm yield survey. So we have to do all of that and evaluate whether the distribution mimics the observed and creating the inputs, the dome for the missing inputs. Now, after you've done that, what CM1 is basically that same setup, including the dome for the overlay, but you run 30 years with current weather, current management, so this is a RAP 0, and no adaptation. Now think about CM1, 2, and 3. So taking that base case, add climate change to it, so that's climate impact from the crop models with current management. Or take the base case of current weather, try out adaptation, which could be the same as a climate adaptation or a different one. The next set of CM4, 5, and 6 are all done with a future RAP. So this, you will need a different setup, fertility, other management aspects, and this will be attempted with the current weather. It'll be in the difference, and then it'll be attempted with the future climate. So this gives the climate change ratio to the farmers, CM5 versus 4. And then will be attempted with an adaptation. So 6 versus 4 is an adaptation attempt. The weather involved will be, for future, will be 2040 to 2069. For all farm sites, there will be 5 minimum GCMs. I'll jump through this. Okay, so the first question is sensitivity of current production system to climate change. So you're taking your current 30-year simulation, running 30 future years. Yield may go down. The next question is what happens to an adaptation applied in the current climate. So this might be something with, let's say that you take the same adaptation under future climate as you do under current climate, but you want to know if it's beneficial now. This might increase the yield. The next question is, what is the impact of climate change on future agricultural production systems? Now, the economist gave this trend line to a future state of the world, but the management will be different here. What is different this time is that the crop modelers will actually run a RAP configuration. They need to do it first with current climate, so that's CM4, and then with future climate to look at impact of climate on production in the future. And that's different from phase 1. Now remember the CM4, we'll try out, at this case, adaptations on the next visual. What is the benefit of an adaptation with climate change? You go from CM5 to 6. So there's some adaptation, say a flood-tolerant cultivar or a good heat-tolerant cultivar from a crop modeling standpoint. I'll skip the next visual. So this illustrates the what will be analyzed by the economics team with the TOA model, and they have questions, and this is why we need 6 crop model runs to allow them to do 4 configurations, because the first one is, what is the effect of climate change with today's management, CM2/1? Their second question is, what is the adaptation benefit under current climate? And that will be CM3 compared to CM1. So that's an adaptation. It may be the same as this adaptation, but it does not need to be. Their question 4 is in the future. So we have RAPs, RAP 1, and the wrinkle here is if you have more than one RAP, the process will be completed a second time. So we're showing you the simple view. So under the future state, here's a base with a RAP with current climate, and CM5 is the RAP with future climate. So that's climate change impact on the future. And then their last question is, what is the effect of an adaptation with the RAP being present? And that's the CM6 versus 5. So this is a review of 4 types of activities that the crop modelers will need to do. One is the simulation of historical conditions, and this involves the farm survey yields, maybe 1 or 2 years. Then to simulate that same setup, except that you'll be doing multiple weather years. So you have a box and whisker that may have to do with weather probabilities. And then simulating the other scenarios, future climate effects, RAPs, adaptations. And new for phase 2, we will be doing a sensitivity analysis that we call CTWN to understand model responses. What I would say from here is if some of you do have a question at this point, I'm ready to go a little bit slower because the first part was sort of an introduction. The next 2 slides will still be a repeat, but they describe what you might need to do to set up the simulations for the historical farm survey. Typically, there's insufficient information to run the models. The models need certain things that or make assumptions that are not safe. I use the word model defaults are not safe, may not be correct. Entering a 0 is not a good thing. So you need, as regional crop modelers, to find the information about local knowledge of soils, crops, and management, and that are not in that farm survey. For the soils, I think you've already done this before, but there are various methods. The APSIS, the Y-Soil database, ISRIC, and S-World if it's functioning. You need to set water holding capacity. The DSAT has a function to do this called S-Build. The Quad UI has a function to do this if you know the sand, silt, clay, organic carbon, and bulk density. There are other methods. You need to worry a little bit about soil fertility, particularly with the DSAT. This SLPF is 1 for the best soils in the world. And in Africa and India, there are many soils that have limitation beyond nitrogen. This would be phosphorus, micronutrients. There's a default shape of the rooting profile. It's conservative. If you have really good soils, you need to make this pattern deeper for extraction. Sowing depth. Now, there are a lot of local agronomists that will have knowledge on what you need to do, so talk with them. The same thing for the variety that may be grown in the farm. What is a variety that's close, for which they may have data, and the data you need include phenology, time to anthesis, time to maturity, as well as a little bit about the growth, yield, and biomass at harvest. Plant population should be in the survey. If it's not, again, local knowledge. Fertilization dates may be there. If they're not, then you should do a split application, somewhere around 0 and 40 days after sowing. And manure application, if it's stated to occur, should be done prior to sowing, because that's quite the typical. So all of this is done with the DOME overlay functions to enter assumptions if the data is not in the survey. One more slide on the typical missing information, and this would be the models start with a certain initial soil water content. If you think the soils are not at field capacity at the start, then you need to do something to set this up. Local knowledge, or if you know it's extracted at the end of the prior season, then start the model at the end of the prior crop and run all the way through the fallow period to let rainfall recharge. Also, initial nitrate done by layer, ammonium by layer in the soils, in the input, the ACE file. Value of 0 is not reasonable. Need expert knowledge. One way to do this is to start the model at the end of the prior season, and then stop it at sowing and just look at those numbers and use those. Another expert knowledge is something that came out of the Global Gridded with Joshua Elliott and the other group. We decided that a simple ballpark was that if you had a certain percent soil carbon, you could assume very approximately that, say, 1% soil carbon equated to a 1 part per million initial nitrate. Okay, so that's the assumption basis there. Prior root mass, prior crop residue, again, 0 is not a good number, even if animals remove most of it. And again, expert knowledge is best, but I would not put in less than 250 for prior root residue, or less than 1,000 kilos per hectare on crop surface residue. There are some guidelines for setting this. If you know the yield levels in the region, and a harvest index is 0.4, then divide yield by 0.4 gives you total biomass, and then assume that 50% of that is root, or that the shoot would be 60% of the shoot, but then you don't have it all there. Assume that animals remove a percentage. All of that residue should be incorporated because that's the tradition, at least in Africa. Not much no tillage, so actually turn on tillage. And the last part is sort of a fussy issue, and that's you need to talk with the soil scientists and the DSSAT APSIM modelers to get help to set the stable carbon fraction if you're using Sentry, or fraction inert with APSIM.
Hi, Ken. It's Sherry.
Yes.
There's a question in the chat from Olivier.
Yes.
Do you want me to read it, or?
Let's read it. I need to otherwise find the corner.
So it's on slide 14. There could be connections in between RAP and climate adaptation. Should we look for those connections, explicitly consider them, or explicitly avoid them?
I think you want to actually, first of all, there are some common elements between a RAP and an adaptation. We will not stop cultivar improvement. Cultivars with improved drought tolerance probably will be happening under normal conditions because it's an ongoing problem. So from that standpoint, you may have a little bit of that happening, but I think that when I'm describing drought tolerance and heat tolerance, if we don't know that exists now, then save that for the adaptation. That may help a little bit. I don't believe we should make explicit connections between the two. An adaptation is a separate attempted intervention. Think about it more as a economic policy intervention to go after a new irrigation region, investment in, major efforts of genetic improvement, that type of thing, rather than the routine cultivar improvement. I hope that helps.
There's also another question. Let's see, we'll get back to it. Can you repeat about soil carbon? This is from FTAB.
Okay. The soil carbon issues. A lot of you, I think, with the DSAT ran the Godwin approach, which basically doesn't even worry about setting the pools. In that case, you may have too much available nitrogen and potentially a little bit optimistic predictions from the sand polymer nitrogen, which is why I think we need to include that topic in the CTWN for evaluating hydrogen response. The APSIM modelers have just one approach, and they have a fraction inert. They have some generic rules for that relative to fields that are either basically out of rangeland, good condition soil, not degraded, crop management where it's under good conditions but relatively used, I say, and then you have land that is quite degraded with low fertility inputs put back in. So you get different types of fraction inert. The fraction inert would increase, or the stable carbon would increase as you have a more degraded soil. The soil organic matter depletes. I think we can give more examples from that when we're in the workshop from some individual experts. I think John Dimes on APSIM can help do that. Cheryl, I'm pulling one slide here from Cheryl Porter's IT, just to show that all of this with the missing information is basically put in using the data overlay, the DOME. For the farm survey field, it's missing, you're providing all the missing information so that all the models use the same information, whether it's APSIM or DSAT. And then later on, when you go to the scenarios adaptations, CM1 to 6, those assumptions still will be there. Okay. The seasonal strategy is used for the case where you need to run 30 years of weather, because you need to have planting date rules, because there's not an actual from the farm survey, specifies climate scenario and the CO2, but there may be other things that go in that. And then if you attempt a new wrap or an adaptation package, then what is embodied in that wrap, a new fertilizer rate, new cultivar linkage, plant population, those things will require relatively a new overlay to superimpose that management or cultivar trade.
Hi Ken, one more question
So
from
the patterns to, yeah, yes.
So Patricia asked, you talked about tillage. Will there also be an option to say up when tillage effects will have, say, on the water balance? I'm not quite sure what that is.
The DSAT already has an effect of tillage to change soil bulk density and infiltration, so the models do that, Patricia. So that's why it's important to say whether you're going to do no-till, in which case the residue is on the surface. In most cases, the farmers do tillage, and you need to specify percent tillage. And as soon as you specify tillage to some depth, that basically stirs up the soil and changes bulk density. And it actually, in the DSAT, changes mineralization rate a little bit. So we need to mimic the observed farmer management relative to that. Rice may be a little bit unusual. I think, well, puddling is there, but the other aspects of tillage probably do nothing. Okay? I'll go back to the conducting the survey data. The whole process involves first entering the survey data and then finding it, but then entering the field and the soils and the weather into this survey data template that Cheryl and the IT team developed. You need to apply those assumptions that I talked about, the missing information in a field overlay. Something that's new is called the linkage file, and that's a connection between each survey site and the DOM that's used. I think linkage in that case will be on a, if there's 100 farms in that survey site, there's one linkage correspondence there. The ADA utility saves the files in a CSV format. And the Quad UI does the conversion to format ready to run the crop model. Then you run the model for historical. Now there will be some feedback. You've already done this, but there are error reports in the Quad UI. There are also error reports in the crop models. You need to get past those problems. Somebody needs to mute the microphone. It's okay. And then once you have output, you use the ACMO to combine the output with metadata, and then there's a saved acmo.csv file. These steps could be repeated several times, especially from the assumption to the final point, if you're changing things that deal with initial conditions. The tools are located in the AgMIP toolshed, and I'll skip over that. Okay. You've created the model-ready files with Quad UI tools, simulated, and then look at the mean and cumulative probability distributions. Now, the goal that you want is to have basically the same mean and shape of this cumulative probability distribution. Now, the reason the crop modelers want to be there is that you will be talking about these yields and the responses to water and nitrogen for that reason. So you need to know that it's a reasonable representation, even though the economists only use the climate change ratio. I'm going to jump to the next visual first and then come back to this. Here's an example for peanut at Nioro, Senegal. So here is yield on the x-axis. The blue is the observed distribution of yields from farm fields, pretty wide. There are two models here. There's the DSSAT peanut model and the APSIM. Now, in this case, you would like to have a distribution that mimics this distribution. I'll come back to reasons that it may or may not be there, and I will back up one more to slide 22 and discuss some of the reasons. If you have a non-legume and the distribution is too high, then you may need to increase the fraction inert or the stable carbon in the DSAT, or decrease this fertility factor, and also check your initial conditions on nitrate, ammonia, and water holding capacity. It's also possible that your farmer cultivar is not as good as the experimental cultivar. If it's a legume, then nitrogen fixation overcomes the lack of nitrogen availability, but you still may have issues with rooting, water holding capacity, this fertility factor for phosphorus. If the yield is too low, then it's the opposite of these traits. Also, you could have strong tails of a simulated near zero, both in the data or in the model. Some models have germination failures that may not happen in the observed. It changes with water holding capacity, or if you have tails of distribution in the upper end that are not right, and it may be related to genetic potential of the cultivar. So I'll come back to this, slide 23 again, for peanut. Okay, the DSAT in this case is a little bit low. There may be issues here with either not having enough water holding capacity generically, that would tend to push this up, or not deep enough rooting, or cultivar that's not good enough. And it might be the cultivar might need to push up here, or even a low SLPF number. So there's that many possibilities, and you could change those and see what happens to bring the distribution up. The APSIM model is having too little spread. What can cause too little spread? Now, if it's truly a legume, you won't see differences due to soil carbon pools, or nitrate ammonium. But if this was a non-legume, then you might not have enough variation among the farms in that representation. For the peanut, it may be that the water holding capacity of the soils used is not showing enough distribution. So there are many possibilities, and these are attempts at giving advice. Here's an observed yield distribution from Farm Survey in Kenya on maize, and this shows that there are a number of farms that have very low yield, 30% of them, and then the yields start moving up, and some very few farmers have high yields. Now, why would you have the failures here? Failure to have emergence at sowing, but here's a small positive. That would be either due to having very poor water holding, well, actually in the farm, or low nitrogen. And this is real data, this is not simulation. But you want to mimic the observed yield distribution to have some realistic believability that you're predicting for that region. So if you had strong left tails, too many failures of simulated, then you would need to ask questions about what did you do with initial soil water, and the CERES maize model does have failure of germination, or the rooting was not deep enough, or the water holding capacity was too small. If you get too many low but positive yields, and this relates to the same condition of having too low initial soil nitrate, water holding capacity causes reproductive failures that create a very low yield. If you have too much or too little in the upper tail, that is more the genetic potential of the cultivar. I don't think I need to cover this one again, other than to illustrate that we will be doing a new set of simulations for RAPS CM4, and I think that's where I'm going with this next presentation. Okay, look at the middle of this, the second paragraph. What's new in phase 2 is that the modelers will attempt to mimic the management genetics of the technology trend. In phase 1, the technology trend came from survey and from impact, and in some cases it was too high, maybe a twofold yield increase proposed, and it was outside of the range of what was feasible from say a physiological standpoint. I see opportunity here to develop modeling papers to actually project a technology trend. So you need to do a visual, what's called a virtual cultivar improvement, hypothetically increasing nitrogen, plant population, other traits, cultivar traits. Now, why is this important? Because cultivars, why is it important to be doing the simulation of the RAP and then climate change with that RAP? The model with high nitrogen, high population, will be, and improved cultivar will be more sensitive to CO2. It'll get more response if conditions are good, but less if conditions are poor, and more sensitive to rainfall. So I think the climate change ratio will be different from what we did in phase 1. Okay, now back to what are specific adaptations. This is a review again, so maybe I don't need to do this, but the one aspect that I would like everyone to attempt, and that is for the cultivar to attempt to take a good cultivar here, and if it's too early in maturity, anthesis maturity for the cycle, to try to bring back exactly that date of anthesis and maturity. This is an adaptation that has not been done in many of the papers so far published, and I think it's an opportunity to do that. But let me jump on to CTWN. We have about, are there questions at this point?
Yes, Ken, there
Sherry,
are. Yep. So Wei and Meng have a question. There are some specific adaptation measures, such as plastic film on maize to increase soil temperature and keep soil water to cope with drought. Do crop models have ways to simulate such effects on environment and crops?
Do they? Okay. Yeah, plastic mulch would be sort of a heroic effort. I know it's done in northern China. In one case, it changes the economics a little bit because you need more labor, you need more inputs of the plastic. So I would call that an adaptation, not necessarily a wrap, although I know it's being done in China. The models right now cannot do this in most cases because the plastic basically stops the soil evaporation, and the models are not set up to necessarily make that be zero. Now, they could do that with minor change, but there's one more wrinkle to that. When you put plastic on the soil, you stop the rainfall infiltration, unless Ming's describing one that the rainfall falls through, and the models are not ready to do that either. We have a preliminary version of the DSAT for plastic mulch production, say of tomato, but that even changes the nitrogen leaching. So I'm not convinced the models are ready to do this in this cycle, this phase 2. Another question?
There's a comment from Jim, and that is the soil C effects are so important that it would be a good idea for the DSAT and APSIM modelers to review what each team uses for stable or inert C to help ensure consistency across teams.
That's an excellent point, and possibly we should drag that into the CTWN, okay? Because there's response to nitrogen, and that response to nitrogen is conditioned by the kickoff of the soil carbon pools for non-legume like maize or rice. So it's possible that instead of having, it may be a fertilizer N with 2 different methods of initial of soil carbon to determine the impact. It would add another wrinkle or complexity to the CTWN. We should discuss that some more in Zimbabwe. Another question?
That's all for now, Ken.
Okay, I'll go through this and you may have questions on this too. The CTWN is an exercise that will be done on a single farm site. Okay, one farm from your survey. We'll have to talk about which one. We'd like something that, a farm that is a typical representative one that's somewhat in the middle of the range. We will do 30 years of simulation of weather and look at effects of CO2, temperature, rainfall, fertilizer, and also do a C3 and P. The point of doing this is that we found differences in APSIM DSAT model predictions for some of the different climate scenarios, and we need to understand how the models differ against individual climatic factors, including nitrogen, and understand what's happening. The goal here will be to plot yield and other variables such as transpiration or ET against these factors. And I'll show examples of that, box plots, and there's a C3MP method with two-dimensional plots. My thought right now is that we'll do this only with maize because there's 5 teams that are using maize, 4 in Africa and 1 in South Asia, and 3 teams that are doing rice. I think this will engage at least one group out of each team. And I see papers coming from this with multiple co-authors, 1 per crop. The CO2 levels start at 360 to 720, and this is the same as what the crop-specific teams did. I want to do this under low nitrogen and high nitrogen. The temperature response from -2 to +8, and this will be on top of your ambient conditions, and rainfall varied from 25% all the way up to 200%, and fertilizer nitrogen from 0 up to 210 kilos per hectare. Those will be separately done from the standard C3MP, so C3MP analyses can be thrown right into their prior structure and method of analysis. We will have dome overlays for the current conditions, but there'll be a batch dome to allow this, and we're setting that up. It might look like this for CO2. This would be a batch dome. CO2 level at 30 kilos of nitrogen, CO2 step at 180, temperature range, and this might be rainfall. Nitrogen is not shown here. The batch for the C3MP is they're not randomly selected, but it's the structured set of variation in CO2, temperature, rainfall. This is what I hope the plots look like. This is from the AgMIP workshop in Brazil, Campinas, but you need to have the x-axis as temperature, for example, and you'll have 2 models. Here's the CERES and APSIM for yield. Do the same thing for biomass. I think there could be or should be a small box and whisker that shows the interannual weather availability for each model, but we'll have to try that out. You might also show ET or life cycle against temperature. And in this case, the lower ET driven dominantly by shorter life cycle with rising temperature. In Brazil, Alex Hinneman also did, actually, APSIM Ariza and CERES rice. So those are exactly the 2 other models that we'll be looking at, and this would be yield response to temperature, to CO2, rainfall. I think that most of the sites are paddy, so response to rainfall will not be helpful. Also, don't look at this one for our APSIM. I think for some reason there was something that CO2 was not turned on. I know that Ariza is sensitive to CO2. But you would show the life cycle. This shows that the 2 models have a very different life cycle under rising temperature. And you can look at biomass or leaf area index as causes. So the goal is to understand what is causing the yield variation. You may even have another one where you have nitrogen uptake against nitrogen applied. I think I probably need to skip through the next few. This is done in Ludhiana. Done at IXIM, one of the workshops, evaluating 3 wheat models. These are rice. Sorry, rice model response to temperature. And the next one is wheat. And basically the models are agreeing here, but so the temperature response may be okay. I think it's more so the CO2 and or nitrogen response. I would also like to see some attempt at plotting the two models with time series. Here's an example of that. I managed to create a visual where these are not very different. CERES maize and the IXIM maize for 1982 data in Florida. But the model's calibrated to both to this experiment, so they should be relatively similar. Do the same for leaf area, ET, nitrogen over time, because I expect, especially with APSIM DSAT, to differ. This shows nitrogen accumulation over time with the CERES model and the IXIM model, and they're different. And I expect that to be true of APSIM and DSAT for maize. This is a slide from a workshop in Kenya at Katumani with long season and short rainy season production. But if the crop is unfertilized, the yield distribution is relatively small, from about 0 to 600 or 800. If the crop is fertilized, there's a huge range of yield distribution for the 30 years of weather. And that's because the yield, when rainfall is limiting, yield comes way down, and if rainfall is sufficient, you get high yield. So yield variability from rainfall is greater. If it's fertilized, it will be greater, and the response to CO2 will be greater if it's fertilized. So this is the reason we need to start off with a future RAP, RAP 1 or RAP 2. This is C3MP example. Alex may have shown this already in the climate scenario. This is for peanut, but what he does is takes those 99 simulations, and there's a mathematical hypercube emulator. So the star represents current condition, and this would be grain yield if peanut if the rainfall increases or if temperature increases. This would be CO2 response from this point if CO2 increases, so more green means higher yield, or rainfall increasing. And the same thing for response to CO2 and temperature. Now the crops differ in their response. If you look at crossing one of these lines is about a 10%, so doubling of CO2, not even a 10% increase in maize yield. For the rice and the wheat and the soybean, 1, 2, 3, 30% increase for rice, and wheat and soybean look like they're greater than that. So that's the point of looking at C3MP, but we also need to understand the single factors, especially the nitrogen. This is from the emulator, the percent yield response to mean growing season temperature. These come from all the different models and sites. Now, from data I've seen on rice and sorghum, there should be 0 grain yield at 35 degrees. What's interesting is their predominance is going that way, but they're not all agreeing, so we would need to understand what's going on. This is absolute yield response to rainfall. A lot of scatter, and that's because the pattern is not known, and a lot of other variation. Site effects on fertility. If you normalize this to percent yield response, then you see that you need roughly 3 to 4 up to 5 millimeters rainfall per day to achieve in effect a yield potential without reduction. So here's a conclusion slide. We need to have the team select one representative farm per survey site. We'll be running 2 maize models or 2 rice models using DOME tools that IT will be helping to create, and climate is also involved in this. We will do single factor response to CO2, temperature, nitrogen, rainfall, where both crop models have to be on the same graph, possibly box and whisker to show interannual variation per model. And we are working on tools for doing the plotting. to extract from the AgMIP files and create the graphs. We hope to have that ready by we need to have it ready by the time of the workshop. We'll do two-dimensional response with C3 and P tools. So what data do you need for each site? Model files to run the crop models, file X if you do it that way, and the soil file and the weather file. But actually these are embedded in the ACE CSV files ready to run. It would actually, and I haven't talked to Cheryl about this, but I think we would like to pre-run the setup for each of your locations if we can, to actually test that it runs and to test the analysis tools. We'll talk more about that and get back to individual participants. Sonali, Alex, and I will help, Cheryl and I will check this out. So that's the last slide. Are there questions? And I'll see if I can see the chat box.
Ken, yes, there's a couple questions. Yeah, Ken, can you hear me? Hello?
Yes.
So Aftab points out or asks, point not clear, 6 crop model runs required to give 4 change ratio values to economic analysis. 4 change ratio values are not clear. Aftab.
Okay. You're talking about where you have a single site in CM2, for example. You would have 5 climate scenarios. Is that right? Let's see if I can find the question. Maybe I can see it. 6 crop model runs for 4 change ratios. Okay, yeah. See, the economists are doing a contrast, and that contrast requires 2 separate cases. One case is the baseline weather, and then second case will be climate change. So that's the CM2 climate change ratio compared to CM1. So that's why they don't match up 1-to-1. So look at the slide and understand what the one slide that had the economist 4 cases, and on the right hand side describes the crop model run ratio that's used for that. Subhash, any criteria for selecting the representative farm? Is it following recommended management practices? I think you would want a farm that is in the roughly attempting the management practices. One where the yield is not, you don't want the highest yielding because they use high nitrogen. You want more representative from the nitrogen and from the water holding capacity and from the management, I think. So maybe not recommended, maybe more representative among the farm site. See if we have more questions.
I have a question, Dilys.
Yes, Dilys, go ahead.
Yeah, about the sensitivity analysis. You're considering rainfall as a factor.
Yes.
With our area, the water holding capacity of the soils are quite low.
Yes.
So I'm wondering if you are increasing percentage beyond 50 up to 200, I mean, you'll be losing a lot more nitrogen through leaching.
Absolutely.
So
okay.
Yeah, so I'm wondering if we could be allowed to limit it, or we can do it for the purpose of records.
Well, I think that's a case of understanding what the model simulations do. The DSSAT APSIM may have the same leaching. They should, but they may not. So you bring up a good point. you may actually have yield being reduced with the high rainfall because you have nitrogen leaching.
Yeah.
But that is part of the explanation process that you need to help us do for your site and you as a representative APSIM modeler. And I would say the same for DSAT, CERES maize. They remember that you're doing these as separate factors. So if you're doing fertilization response, you'll be doing it with whatever the rainfall was for that representative. Well, it will be over the 30 years, okay? So you're taking the historical pattern. So some will be high rainfall, some will be low, and that will give you a variable response to the nitrogen. I think it's okay. You bring up a good point that we need to help right in the analyses, in the results.
Yeah.
Okay.
Okay.
Anybody else? Yeah, Dillies, we will be counting on you. We're somewhat short on APSIM experts, so John Dimes is supposed to come, but you and Subhash represent the more of the APSIM experts.
Okay. We'll be available to help.
Okay.
Yeah.
Other questions?
Yeah, maybe can I ask one more question? Ken?
Yes. Go ahead.
Yeah, so are we alternating each factor at a time, or it will be in combination with the others?
Okay, none of these will be in combination. They're single factor. There is one case where there is. The CO2 response will be done at low nitrogen and high nitrogen because we think that's already important.
Okay.
And actually, you bring up a point. We should investigate this, and once we have set up our system, we may find that we need to analyze some interactions. So we need to keep our eyes open for that.
Okay.
Ken, can you hear me?
Yeah.
This is Alex. Can anybody hear me?
Yeah. Can you speak up? I'm not quite hearing you.
Sure. Maybe this is better. This is Alex here. I had to join late. I'm sorry about that. But if we're doing the C3MP sensitivity test, those are multi-factor. There you will have temperature and rainfall